Well, looks like we're at 12 o'clock, so I'm going to go ahead and get us started. So good afternoon, everybody. I'm Jason Gibson, CCO at IACMI, the Composites Institute. Innovation Insights is our monthly webinar series highlighting the people, the ideas, and the partnerships driving advances in composites and manufacturing across the U.S. As part of the Manufacturing USA Network, IACMI leads national efforts to scale new materials, develop sustainable processes, and strengthen U.S. manufacturing competitiveness. At IACMI, our mission is to convene, connect, and to catalyze. We convene the composites industry to share ideas and opportunities, connect industry, academia, and national labs, and catalyze real progress through collaboration and commercialization. Today's Innovation Insights reflects that mission, highlighting the new ideas, the technologies, and applications driving the future of composites. For those new to IACMI, we accelerate composite innovation to strengthen U.S. manufacturing and workforce competitiveness through co-funded projects, access to world-class facilities, and a powerful national network. If you're interested in listening today, you're not currently an IACMI member, we encourage you to consider the value of joining. When you join, you'll be part of a network that brings together peers from industry, academia, and government, all collaborating through our working groups to shape where composites innovation is headed. Whether you're a startup, an OEM, or a supplier, there's real opportunity to get involved and make an impact. We'd love to have you join us, so please visit our website and reach out to us by filling out the online form. And if this is your first time attending, we encourage you to explore past episodes that are available on our website. Since its launch, the series has brought together a wide range of members and partners, each sharing real-world applications, technical advancements, and valuable lessons learned. Our goal is not only to keep you informed on the latest trends in composites and advanced manufacturing, but also to provide a direct connection to the thought leaders and innovators who are shaping the future of this field. And today is a good example of that. So let me introduce our speakers for today. Today's Innovation Insights brings together three distinguished presenters advancing the state of composite materials, manufacturing efficiency, and design innovation across multiple industries. We'll start by highlighting scalable solutions in lightweighting and process optimization, then explore how next-generation press systems are achieving unprecedented throughput and energy efficiency, and then we'll conclude with a case study demonstrating innovative molding techniques for thermoplastic structures. But we'll begin with Kevin Cain. He's the Chief Technology Officer of Aria Group, who will introduce Aria Composites Technologies, a newly launched subsidiary dedicated to accelerating innovation in composite design, engineering, and manufacturing. Kevin will discuss how ACT leverages 3 decades of experience in high-performance materials and processes, from Prepreg and Infusion to resin transfer molding, to deliver advanced composite solutions across transportation and mobility sectors. And just as a coincidence, you'll also see an article out in Composites World today around Kevin and his group. Next, Ted Patchell, Sales Manager for Hydraulic Systems at Andritz Schuler. He'll present composite presses that deliver more with less. Ted will showcase how Andritz Schuler's high-precision press systems, from 10,000 kilonewtons to over 160,000 kilonewtons, enable flexible, energy-efficient production across SMC, BMC, and RTM applications. His session will highlight how these systems reduce cost and waste while increasing manufacturing consistency and scalability. And then to close us out, David Okonski, Deputy Director of IACMI's Scale-Up Research Facility, will share insights into using water assist to lightweight an injection molded part. David will describe how water assist injection molding, an underutilized but powerful process, can significantly reduce mass and thermoplastic components. His case study will illustrate how this technology was successfully implemented at SURF to produce a production intent cross-car beam with substantial weight and cost savings. Now, before we jump into it, just a quick note. If you'd like to ask questions, feel free to enter them in the chat. We'll be taking a look at them, and then if there's time after each presenter, we'll ask those questions of them. So with that, I'd like to turn it over to Kevin Cain. Kevin, if you'd like to share your screen.
All right.
Yep,
So
looks good.
Yeah, good there. Excellent. Okay. Well, my name is Kevin Cain. I'm really excited today to introduce everybody to Aria Composite Technologies. So I'm the CTO and one of the co-founders of Aria Group, along with my partner Clive Hawkins. We founded Aria back in 1995. We're privately held, have 85,000 square feet of facilities, primarily located in Irvine, California. I head up an engineering group here in Traverse City, Michigan, and we have around, over 100 employees. And just before I jump into, what ACT, Aria Composite Technologies, is up to, I want to give everybody a little background on Aria Group and what we've been doing for the past 30 years. So in 1995, we founded, through Clive Hawkins, myself, as a kind of an engineering and low volume manufacturing, prototype manufacturing consultancy out there in Irvine. And some of our initial clients were like Panos Esperante, a really interesting low volume aluminum intensive vehicle, the Rodman Pikes Peak race car. We did a lot of the design and manufacturing for the Las Vegas monorail. A large number of our early clients were the OEM automotive design studios on the West Coast. So that includes like the Honda SUT, Ford GR1, Mazda Fury. And then into the early 2000s, there was a lot of electric vehicle, startups were happening out in the West Coast. And we were a major resource and development partner for many of those firms. Really, noticeable. The very first Tesla Roadster that existed in North America, we produced the body panels for that here at Aria Group. Worked very closely with Fisker throughout the years, Aptera, and again, continued our close relationship with Tesla on the very first Model S hard model was also done at Aria Group. In 2008, though, there was kind of a pretty major setback to the automotive industry through the, 2008 recession, and Aria Group pivoted, and we produced a lot of interesting projects for the entertainment space. So we were working with Hollywood out here in California. So we did major, big, budget motion pictures, Avengers, Transformers. So did, a number of large, projects for that. But one that was really kind of the most interesting and notable for us was our collaboration with Disney. So in that era, Disneyland was expanding with the Cars Land theme park, and part of the programs they had was Disney's Flying Tires. It was Luigi's Flying Tires. It was a ride where you kind of floated around on basically this giant air hockey table, and you had to fly around on this floating tire. That involved a tremendous amount of prepreg composites. It was very challenging to get the structural requirements into that lightweight of a structure that could still carry, passengers and meet Disney's demanding 30-year, lifespan duty cycle. And that got Aria into serial production. So we kind of moved away from just doing a single prototype into doing low volume production. And that's what continued in like 2015. So we started doing like the first 150 Singer Porsches. All the bodywork that's prepreg carbon fiber on those vehicles, and all the paint is done at Aria Group for the initial run of those. We worked with Zinger, Rezvani, and another client was Uber. And when they were doing their autonomous vehicle, the XC90, we did like the first 400 LiDAR sensor caps for that project. And the Uber connection is very interesting because right at that point came out the Uber Elevate white paper. So that was them introducing the concept of air taxi to the industry, the whole eVTOL market. And that got us connected with Joby, Supernal, Whisk, a lot of these startups in the eVTOL space. And we saw firsthand the manufacturing challenges that they were experiencing trying to do a lightweight composite structure, but at rates that far exceeded what aerospace was, had any expectations of doing. So it was right around that time that we had really internally began focusing on how to achieve higher rate manufacturing in composites. And so in 2025, we have founded Aria Composite Technologies. And some of our, partners, initial clients that we're talking with right now and solving their composite manufacturing challenges is Whisper Aviation, Tello Trucks, Auto Aviation. And internally, we did a proof of concept demonstration project, which is the Exafuse chassis. And I'll be talking more details on that in just a few minutes. So again, in 2025, Aria Group has split into 4 standalone companies to better meet our client needs and prepare for future growth. So we have Aria Low Volume Production, Aria Composite Technologies, Aria Aerospace Technologies, and all of these are backed by the Aria Intelligence. That's our own internal um, paperless communication system. So within Aria Composite Technologies, we are immediately, have capabilities due to our, 30-year history coming from Aria Group. So we have, 20,000 square feet dedicated just to composite manufacturing in Irvine, California. We have a large team already, who's been working for decades in carbon fiber, fiberglass, hand layup, prepreg infusion. We are, again, very experienced in doing, high quality finished parts, whether it be single runs or, into the dozens to hundreds of components. We do our tooling, design, and manufacturing in-house. We have engineering teams able to immediately provide engineering support. All of this is centered around our paperless workflow based on our operating system, the AOS. And in combination using AOS, we just recently got awarded our AS9100 certification. So that's looking to really expand our efforts in the aerospace industry. We have like 9 5-axis mills, CNC cutting table, a strong relationship with Stratasys. So we have 3D printers on site. We've got a large format curing oven. We have a good sized autoclave, clean room, all the, and again, fully equipped surfacing and paint department. But the mission of why we do this, why we've set up Aria Composite Technologies, is that our goal is to commercialize breakthroughs in composite research and development into scalable solutions that overcome the barriers limiting widespread adoption of composite manufacturing. So that's where we're really excited to be talking with other companies within IACMI over who has some unique, manufacturing processes, some new technology. We really want to be your partner in finding the right clients for those and bringing it to market. Our first example of this is Exafuse. So on September 30th, we launched our Exafuse process at the Up Summit in Bentonville, Arkansas. And what you're seeing there is our proof of concept single monocoque tub that we produced internally using the Exafuse approach. So Exafuse is just a breakthrough in composite manufacturing where we believe we're going to deliver high-rate, cost-efficient productions of large integrated composite structures, leveraging ultra-low viscosity resins that provide a low-pressure, fast curing process. This is going to give us scalability, cost reductions, improved sustainability, and still meeting high-performance targets. So to approach that, we're taking moving away from the traditional hand layup, what you see on the left-hand side, somebody tries impregnating the resin into the reinforcement, and also avoiding some of the money that's been spent on the high-pressure closed molded processes. Because with Exafuse, we have a resin that flows like water but can cure nearly instantly. They're tougher, lighter, and more recyclable than any of the thermosets that have been used before. And using that type of resin system really, what we're excited about, it unlocks true part integration. You can use these to achieve design freedoms that have never been possible before with advanced composites. So what Tesla sort of demonstrated with the gigacasting approach of taking, dozens of discrete components into a single casting, we're using that similar design philosophy to take dozens of discrete components and do it into a large format integrated composite structure, but without exorbitant capital expenditures into massive presses or tooling. And also that's unique with the low viscosity resin systems. We can do secondary features of ribs, bosses, molding clips directly into the resin system that's integrated in the same molding step as you're doing the composite reinforcement. So all of this is going to accelerate our production rates. We're looking to achieve production rates in the thousands of parts per year. And a lot of that's also going to rely on dry fabric preforms. So that's going to be key to material handling because we're looking to have, automated roboticized material handling to go through. And so the entire tack time, it should be under 15 minutes to produce a large, tub as we saw with that initial proof of concept. So just kind of reiterating what our Exafuse's benefits: design freedom, really large format, complex shapes. You do achieve an excellent part surface quality right out of the mold. Its infusion times can be less than a minute. Lower pressures are required. It's highly automated process, and it's a still very tough system. It's fatigue resistant, and so again, we're really excited about the benefits that we're seeing with this, and that's due to our strong collaboration with ExxonMobil. So the initial resin system that we're demonstrating for within Exafuse is the Proxima system, and that's something that ExxonMobil has recently been bringing to market. So we've been within ACT have been working with them on finding the best use cases and designing solutions that really take advantage of the resin chemistry and see how far we can go with it. Last year at JEC, ExxonMobil had on a stand this concept battery box, which was showcasing integrated ribs and gusset features on top of a continuous woven fabric reinforcement. So Aria Group helped, design that component there. And we're really excited to be working on future development with IACMI Surf facility outside of Detroit. ExxonMobil is going to have a Proxima customer collaboration hub that we're really, excited to be a part of. So again, looking at the specific tub that we did for Myers-Manx, our objectives were to, reduce cost and weight for the program, shorten production time, lower bomb count, still have enhanced corrosion resistance, minimize capital expenditure was a key part of our study, and achieve over 5,000 units annually. So we were starting with them with a welded aluminum tub. So this was they were using the flat laser cut aluminum sheets to be tabbed and slotted. It was very low capital investment, but it took 4 days tack time, a lot of manual welding, over 135 pounds, and we were able to combine that down into just a firewall and tub, and that was just two parts. Before even using our prototype tooling, we were seeing like a 20-minute tack time, and it got a weight reduction of 75 pounds. We were able to bring this whole assembly down to 75 to 100 pounds. These are some photos just kind of demonstrating internally our tooling process, machining the masters, polishing the masters, prepping them, to doing the composite molds, reinforcing the molds, and that achieved us to get this is our very first trial with the full-size tub. And again, it's around a 15-minute infusion, and using this resin system, it requires about an hour cure, but we'll be looking at production systems which have enabled a snap cure process. Here are a few additional photos showing the finished component. And so this is, again, our initial proof of concept tub that we've done for Myers-Manx. They're our design partner as we're working through this program. And we're all very excited about the result of this. Extremely, extremely promising. So in 2026, we are going to be moving from this proof of concept into a high rate production proof phase. And we're going to demonstrate our target cycle times of less than 10 minutes end to end, and also have our financial analysis that really validates our cost projections on here. So again, ACT is looking to commercialize new advances in composites research. And so I'm asking any IACMI members, anyone else out there, if you have technology that you think that ACT can help you demonstrate and bring to market, please reach out and contact me. Thank you.
Thanks, Kevin. I got a quick question for you. How much or how would you like to get involved in the design process? In other words, are you able to do laminate schedules and help specify
Yep,
all that? Yeah, give us a feel
absolutely.
for how
No,
you'd like to work that out.
yeah, no, absolutely. We have a lot of experience with that. We're very accustomed to clients coming in with a little more than a paper sketch, a little, the traditional napkin sketch, and working out with our engineering team all of the, load requirements and, FEA analysis, lifespan analysis, and doing all the B-side engineering into tooling. So that's something that we're very accustomed to. Within Aria Aerospace Technologies, we, kind of expect there's going to be a lot more build to print within that group. But within Composite Technologies, we're really eager to kind of help customers, design their solutions.
Great. Well, thank you for that. With the time where we're at, let's go ahead and turn it over to Ted to learn a little bit about the Andritz Schuler pressing and the capabilities that they offer. It looks good. We just need you to come off mute. Oh, you're still on mute, Ted. There
Oh,
you go.
is that good?
Yep, we can hear you.
All right, sorry about that. Hello, everyone. For those of you who don't know me, my name is Ted Patchell, and I am the sales manager at Andritz Schuler Inc. for new hydraulic press equipment. Before I get started today, I'd like to thank Kim and the entire IACMI team for allowing me to present today, and thank you all for listening. During my presentation today, I will be going over the relationship between Andritz Schuler and our parent company, Andritz. Then I'll be going through the different types of Schuler composite presses we have available, into a deeper dive on the short stroke compact press design, like the one that is being reinstalled at the SURF facility. Then I'm going to go through our competency in high precision presses for quality parts, and wrapping up with a few turnkey manufacturing lines as examples that we have provided recently. I'm sure that a lot of you are familiar with the Schuler name and brand, but Schuler has actually been a part of the Andritz Group since 2013. We have gone through some rebranding here in the last year, so you're going to be seeing a lot more of the Andritz name, both on our equipment as well as at conventions. What this means for us is that we have a greater access to the many resources of Andritz Group in its portfolio, which has already proven to be beneficial in advancements in both our digital technology solutions and our battery department. Andritz Group is an international technology group that's headquartered in Austria with a strong foothold in pulp and paper, hydroelectric power, green energy solutions, and our division, which is metals. Schuler makes up approximately 80% of the metals division and holds a strong position in the press market. Within the Andritz Group is a vast network of companies and locations that span the globe. This includes over 30,000 employees in over 80 countries. This network has allowed us to consistently stay close to our customers and to gain additional perspectives. Within the Andritz Schuler Group itself, we have a vast network of manufacturing and engineering facilities. And these facilities and our customer relations are heavily strengthened by our extensive service network. We offer regional service support located across the United States, and we have also recently acquired an office in Canada. This allows us to respond and deliver quickly for any issues that may arise and to support modernization projects on older press equipment. On Michigan Avenue, which is near our Canton, U.S. headquarters, we have a service shop that includes a pit and is capable of manufacturing and servicing spare parts and press repairs. And as many of you know, our service team is currently working out at the IACMI SURF facility to reinstall that 4,000-ton short stroke press. I will now dive into the main press designs that we have for composite applications. While each project that we undertake is unique, the majority of composite presses that we produce fall into one of these two categories. The first being a classic long downstroke press. These presses are very similar to ones that we produce for automotive stamping, for deep draw, for a multitude of other non-specific hydraulic press applications. The second style is the compact upstroke press, the one at the SURF facility, and it utilizes a locking mechanism for the upper slide and creates the compression stroke from underneath. Here you can see the stark differences between these two styles of press. The classic composite press on the left has a hydraulic system and the accumulators all stacked above in the crown, whereas most of this is contained and I apologize for the cutoff section of the picture on the compact design here in the pit. While they both utilize slide cylinders to open and close the mold, the classic press uses these for the entirety of compression force, where the short stroke press has all the cylinders underneath. Both press styles are extremely flexible in table size and press force and can be adjusted based on the die requirements. Of course, both press styles have their pros and their cons. The classic functions very well over a full spectrum of press forces, but is not ideal for the thermoplastic applications or in buildings with lower ceilings, as the crown takes up a lot of space. It is also less energy efficient than the compact design. The compact design functions well for both thermosets and thermoplastics due to its quick closing speed, but it does require a very large pit foundation. It is also not as efficient when you get into the lower tonnages, around 800 tons and below. Here you can see the stroke cycle of the compact press. The slide is able to travel rapidly downward until it reaches the predetermined locking position. Once in the locking position, the hydraulic clamps lock the upper die into place. These clamps are locked simultaneously to ensure symmetry during the process. After they're locked, the working stroke comes from below and dwells in working position for the necessary part-specific time, and then is returned to its home position. Some additional benefits to the compact short stroke press are the ability to produce quality precision parts utilizing an adaptive congruent bending lines and parallelism control. The adaptive technology also allows us to change molds quickly without any additional modifications. The rapid travel of the upper die allows us fast closing speeds. This combined with a short pressure buildup time creates a system that is effective for the thermoplastic applications. Our position indexing and parallelism controls are highly precise, and adaptation is not required based on the mold's height. From an operating cost standpoint, the short travel of the cylinders creates a more efficient production with significantly less oil compression, and we can utilize selective cylinder operation to further reduce your energy costs. Here are a few examples of some multifunctional compact presses. These are the short stroke presses designed for R&D departments across the globe. We have the one in England at the NCC. We have one at Aachen Center for Integrative Lightweight Production. Of course, the IACMI press. There's an OEM in Korea utilizing it for R&D, as well as Unist in Korea and Asklawo in Germany. Here at Andrews Schuler, safety is a main priority for us. Our builds exceed many standards and regulations, especially when combined with a mold scanner. We can create different safety zones to detect people anywhere inside of the enclosure. We also prefer to install a transparent enclosure with access doors and light curtains in place. With the transparent enclosures, it allows you to have full access and sight of the mold without putting anyone unnecessarily at risk. Here is an example of the modular design of the short stroke compact press. Because of this, we are capable of expanding the press size with a reduction in the engineering costs overall for the larger presses. The largest one that we have produced currently is 16,000 tons, but we do have further capability for expansion if somebody's project requires it. Now I will get into the congruent bending lines. With the traditional non-congruent bending lines press structure, the deflection of slide and press plate are curved in opposite directions. This creates limited control on the part thicknesses, and it increases the thickness in the center of the press. Using our innovative adaptive congruent bending lines, we are able to achieve wall thicknesses with increasingly tight tolerances and capable of optimizing the bending lines per stroke. This technology has been adopted on 17 presses currently, and some more that are under production. In these graphs, you can see that the displacement against nominal becomes significantly skewed the further out you get from center without using the congruent bending lines. With the congruent bending lines, you see that your finished part ends up much more in line with the desired outcomes. We did a case study regarding these congruent bending lines with an automotive OEM's floor pan, and we were able to modify the original wall thickness that was 2 millimeters by 0.25 millimeters, which was able to achieve a greater lightweighting without any reduction in parts lost due to tolerances. This study also proved that this technology can be adapted and used for part production. Another important technology for our precision presses is the parallelism. Utilizing our parallelism controls is extremely important for the composite press production. With these, we are able to press parts without using hard stops, and we can avoid any issues due to an eccentric load condition, which is nearly unavoidable to have an eccentric load in the composites. This allows us to create tight shearing edges and produce precision parts. These systems create a closed loop of control for both position as well as parallelism. The positional indexing is done for the injection of resin or coating through encoders in the mold that are programmable. They're capable of mold weights of up to 90 metric tons with an accuracy of 0.05 millimeters. Our parallelism controls are operated during the complete process through mold referencing and programmable tilting. Our parallelism controls are capable of withstanding eccentric loads up to 10,000 kilonewton meters with an accuracy up to 2 millimeters. Alongside these, we have our HMI technology. This system can be used for a variety of functions, including diagnostic testing and product data. Here you can see an example of our diagnostics page with these easy to read dials that can show you where your issues are arising and can help you to root cause any problems that you have. With this compilation of data, we have a data inspector that can be integrated into the HMI of your system. This inspector allows you to record up to 100 unique digital channels, and you can compare these functions with its powerful graphic data analysis, which is shown here in the picture. Any and all of these readouts can be logged and exported as CSV files, so you can archive them and utilize them for any root cause and tracking situations down the road. Some additional examples of equipment that can be added to our space HMI system include mold temperature and heating devices. These can also be used in tandem with our vision systems or additional applications that you may have. Now I will go through some turnkey composite manufacturing lines that we've produced recently, as well as a collaboration with Fremo. Turnkey lines for composites can be quite complex. There's a multitude of processes and applications, of course, I'm sure most of you are aware of. Due to this, we have been working very closely together with Fremo in Germany. We have a strong partnership with them, and it has helped both parties produce cutting-edge solutions for turnkey lines. Fremo has expertise in front-of-line and end-of-line equipment for composite production, and combining them with our press abilities allows us to create complex composite manufacturing lines together. Here is an example layout of a high-pressure RTM system that we came together with Fremo to design. We can design and modify any of it to include less automation or more, depending on what your requirements are, all the way up to being a fully automated system. And in action, here you can see a wet compression molding and high-pressure RTM press system with the Schuler compact short stroke press. And from Fremo, we have the epoxy high-pressure RTM and wet compression molding metering unit as well as their robots for resin application. Another recent project that we have included in the high pressure RTM workspace is 11 production lines for an automotive OEM over in Europe. Each of these lines is capable of producing 25,000 parts per year with an approximate 6-minute cycle time. And these all include an automatic tool change for quick die changeovers. One quite unique project that we are very proud of over here in the United States, we have a 16,000-ton composite press used for special composite tanks. The customer reached out to us looking to replace their injection molding system and possibly speed up their production. So we created a unique application where the material is put on the die while the bolster is moving. And due to this, we were able to reduce their cycle times and increase the output. Another recent project over here in the US is a 16 set of 3,600 metric ton composite presses. These presses were all customized specifically for the customer and include a great case study of our VDP technology. It's a visual die protection. It's a vision system on each press that analyzes any changes that are inconsistent with the production process, and you can set on how sensitive they are, and they will shut down and save you from expensive die repairs, bad parts. There are many applications, but we found them to be extremely effective. And I think they're going to be used much more in the future here. Thank you all for your time today. I appreciate it. Please feel free to reach out to me if you have any questions, any upcoming projects, or you're just curious. We are happy to do deeper dives on any of our hydraulic technologies.
Well, thanks, Ted. We do have a question for you. This comes from
Yeah.
Ray Bowman. What are the capacities of the Chapu systems that you've deployed?
The largest would be the 16,000, but I don't see that as a limiter. We could build a larger one if we.
So what would be the limits as far as tonnage as well as the die area?
It's a good question. Unfortunately, I don't have that answer for you right now, but I'm more than happy to go talk to our engineers and see how far we can push it, and then I'll let you guys know.
All right. Well, thank you. I appreciate it.
Yeah.
And with that, let's go ahead and turn over to David, our last presenter. And David has an interesting project he did for Ford in the past that I thought was really exciting. And so I thought the audience would enjoy hearing about this technology. David?
I'm happy to share my slides as soon as Ted releases.
Ted, if you wouldn't mind, stop sharing. Ted, are you still there?
I'm working on this to see if I can make that
Okay.
happen. Um,
There we go.
I
All right,
think I
David.
got it to work. You'd want to try that, Dave?
Sure.
Learn something new.
Can you see my screen?
I
Looks
can't.
great,
Looks
thanks.
good. Thank you.
Good afternoon, everyone. I'm Dave Okonski, Deputy Director of the IACMI Scale-Up Research Facility located in Detroit, Michigan. Today, I'll be talking to you about water assist. I plan to give you a description of what water assist is, kind of level set everyone, and then go into a case study that we did at the scale-up research facility with Ford Motor Company. So water assist, known as YM, also known as water injection technique or fluid injection technique. And it's a process, a specialized injection molding process that provides molders with the opportunity to make high quality, lightweight plastic parts in relatively short cycle times. It is a specialty injection molding process where a polymer melt is injected into a cavity with the subsequent injection of an incompressible fluid, in this instance it's water, into the molten core of the part to create a hollow section. It is very similar to the gas assist injection molding process, but it offers a significant reduction in cycle time of up to 70%. When you think about that, with the water, which is cooler than the melt temperature of the thermoplastic, you're cooling the polymer wall, right? Not only from the core, but from the mold itself. So you increasing your flux. The water assist can be made to use elongated parts with diameters that are 30 to 35 millimeters in diameter. It can eliminate the sink of ribbed parts. So you can eliminate the read-through of a rib in a Class A surface by hollowing out that rib and lessening the volumetric shrink. And it can create flat parts with integrated thick and thin-walled sections. So the advantages of water assist is a reduction in your cooling time, your cure time, which can shorten your overall cycle time. You have a material savings because you're creating hollow sections, and you have the potential to reduce clamp force, particularly if you use the short shot method to the water assist approach. And I'll talk more about the short shot method in a few slides. You increase part quality by reducing sink, shrink, and warp, particularly warp if you're able to uniformly distribute the residual stress in the part over the entire part. And you improve the weight-specific mechanical properties because you are hollowing sections and creating geometric stiffness. The simplification of part design by giving you increasing design options. So you can design your part to go from thick to thin sections and not your conventional thin to thick. So it gives you a little design freedom. The caveat there is your tool design can get complex, right? Because you might have to incorporate flow leaders to create the hot cores that are hollowed out. The disadvantages of the water assist process is there's cost. You'll have licensing fees for the different units you may have or purchase. You have the cost of the water injection plant, the equipment, and the controller to deliver the water either at constant pressure or volume. And then you'll have to add added maintenance of the water injection systems. You'll have to keep that up and running as best you can. It is, again, a complex system due to its specialized nature. And so you're going to have to train your plant personnel, right, to deal with the water systems. The complexity comes in the water inject systems, which come in a variety of configurations that deliver the water either at constant pressure or at constant volume. In constant volume, you have two types of systems, one that uses an accumulator and another that uses hydraulic pumps. The constant volume, you essentially have a hydraulic cylinder, right, that will deliver a set volume of water to the injectors. But each of the systems delivers water to an injector. The injector could be a nozzle, either located in the runner system or in the part itself. The nozzle can be rotated to shut the water on and off, or the nozzle could essentially be a pull pin, right, where you pull the pin to release the water and you re-engage the pin to shut the water down. It is preferred to place the water injector in the runner system so that you minimize the cosmetic defects to the part surface, particularly if you're going for a Class A finish. So a rudimentary pictorial of the water assist process, right? You'll have the mold close, you'll inject the polymer, and at some point in the injection, you'll inject the water. You'll then apply a pack pressure through water or the polymer. You'll let the material cure in the tool. You'll release the water and pack pressure. As the screw rotates, you'll reclaim the water from the cavity, the mold open, and the part ejects. So the water assist system, again, can be done in two type of methods, the short shot or the full shot. And I'll give you a little more detail on each of those processes. In the short shot process sequence, the mold will close. The polymer melt is injected so as to partially fill the cavity to 50 or 90%. The caveat, right, is that you have to inject a sufficient amount of polymer melt so that when you start to inject the water, you don't get the water to blow through at the flow front of the melt stream. And of course, at this point, the ram is not bottomed in the injection phase. The water is injected into the core of the polymer that is in the cavity. The water will take the path of least resistance, and water pressure will typically range between 4,000 to 7,000 psi. It's the advancing water front, right, that pushes the melt flow front forward to fill and pack the part. The part actually cures under water pressure. There is no applied polymer pack pressure. And as the screw retracts, the water is retrieved, mold opens, the part ejects, and the cycle is ready to repeat. In the full shot process, the mold closes and the polymer melt is injected to completely fill the cavity. So it's more like the conventional molding process where you're filling to 95 to 98% of full before you start to release the water. The ram, of course, is not bottom because you're still using polymer pressure, hydraulic pressure, to pack out the part. But water is injected into the core, and again, it will take the path of least resistance. Water pressure will be between 4 and 7,000 psi. The water pressure is used to supplement the pack pressure to eliminate sink on the surface of the part. The part cures under water pressure as the screw retracts. The water is relieved just before the mold opens, the part ejects, and the cycle is ready to repeat. There's several variants to the full shot water assist process. So as you inject the polymer melt, or as you inject the water into the polymer melt, right, it's going to displace material from the core, and that material has to go somewhere. So in this case, there's an overspill cavity where the melt exits the actual part into an additional cavity, and that creates the volume for the water to fill. You can also have a melt pushback method where the water is injected literally at the end of the flow, and it pushes the excess melt back into the plasticizing unit. You can use this technique if your polymer melt is hydrophobic, right? In the case of nylons, where it likes water, you really wouldn't want to do this type of process. And you can also do a full shot with a core pullback. So as you fill the cavity, right, the polymer melt fills the cavity, and you can actually release the cores, pull them back, and that will create the volume for the water to be injected and expand and hollow out the cores. This is a pictorial of each of the processes, short shot and the full shot process. So you can see here in the short shot process, we're stopping, filling the cavity short of being full. Water is injected, and that water will push the flow front to the end of flow, filling out your cavity, and then you're using the fluid pressure to pack. The full shot process with the overspill cavity is in this quadrant. You see you're filling the cavity, you're injecting water, which pushes the polymer melt from the core into the overfill cavity. And then you're holding both with polymer melt pressure, pack pressure, as well as water pressure. In the melt pushback, you see that you're actually injecting the water at the end of flow, which is displacing the hot material from the core back into the injection unit. And then the core pooling, you are injecting the polymer melt and then displacing the cores to create the volume that you can hollow out. The part defects that you can see in the water assist is the concentricity of the hollowed out sections. It is usually very good with water assist, much better than gas assist. You can also, if you're using a glass fiber system, you can push fiber out of the material and into the water channel. You can also create double walls with voids or membranes across the water channel, or you can actually have water inclusions into the wall of the polymer outside of the hollow section. So with that level set and giving you a knowledge of the water assist process, I'll go through a case study that we did with Ford Motor Company at the scale-up research facility. It was for a cross-car beam. Cross-car beam essentially is the substrate that holds the instrument panel, right? It is the support of the instrument panel. The instrument panel was a combined design exercise by both Ford Motor Company and their chosen tier one, which is Yangfang. So this is what the final product was intended to look like, with a wraparound display, very similar to what you'd see in a current Ford Nautilus model. This is the actual part, right? The cross-car beam substructure that was molded into or molded at the surf. It actually included much more than water assist. It was a complex die which had part consolidation. There were strengthening sections across the top, reinforcement to add stiffness, and it was actually, there were 14 inserts that were overmolded. So again, not only did it include water assist, it was a complex part that included overmolding of localized support and attachment features. So what was the desired effect to do with water assist was to hollow out and add geometric stiffness around the steering column. And you can see the water assisted channels in this slide, again, around the steering column in this location, as well as the previous. Apologies. Complex tool. The whole project was based on a FOA grant. And the idea was we were going to leverage novel materials and processing methods to demonstrate the feasibility of a more weight-efficient design of an instrument panel using localized reinforcements. And again, those localized reinforcements were a carbon fiber patch placed along the top of the instrument panel, as well as the geometric stiffness added with the water assist channel, hollow channel. The targets for the program was a mass savings of greater than 40% compared to conventional steel cross-car beam, which for Ford typically comes in at 15 kilograms. The allowable cost penalty, again, because we're actually doing more functionality than a conventional steel beam, right? So you're adding cost, right, at the hope of saving mass and production cycle time. So the allowable cost penalty was to come in under $6.60 per kilogram, and we were targeting a cycle time of less than 180 seconds. The tool was complex, more complex than it needed to be. There were 12 valve gates incorporated in the hopes of demonstrating future technologies, future molding techniques beyond the current project. Here's what the actual tool looked like. This is the moving section, the core side of the tool with a part on it. And you can see the over spill channel here that led it to a puck. This is the end of arm tool, which actually not only picked the part, but rotated to place the localized stiffening, if you will, along the top edge of the cross-car beam, as well as the attachment inserts that were overmolded. This is the cavity side of the tool. The water inject system was in this location, and water entered the part through this channel. You'll notice that the tool is not set square to the platens of the press, and this was a 3,000-ton millicron press that was used to make the part. It was not square to the platens. It was angled to allow us to use gravity assist to drain the water during screw retraction, and that facilitated water removal. What were we able to accomplish? So in this particular program, the water assist used the full shot process sequence with a pull pin water injector and an overspill cavity that you can see here that push the core of the hot melt core material into a puck. The initial process setup was established using a glass-filled polypropylene, which then we transitioned into a 40% glass-filled nylon part. And the valve gates, the 20 valve gates, were cascaded from left to right. So cascaded flow is employed to push the melt front across the part, again, from left to right. Approximate fill time was 6 seconds. We were consistently able to hollow out the channel around the steering column, and we saw good part-to-part mass variation with the production intent material, which was a combination of carbon fiber and basalt glass fiber. So in that case, the part came in with a variation of 0.9%. So typically you like to see that below 1% for injection molded part. We had much more variation in the runners in the puck. If that's okay, that material was reclaimed, reground, and put back into the process stream. We were able to process parts in fully automatic mode to demonstrate high volume manufacturing capability, and we made over 600 crosscar beams to support the development work and the physical part testing. The final results, we had a mass reduction based upon this part mass, the highest, right? So the highest of the spread at 50.6%. Again, the target was to achieve greater than 40%. Our cost penalty came in at $5.43 per kilogram, less than our target. And our cycle time during the run at rate was 167 seconds. The target was to get less than 180 seconds. We subsequently followed up with additional molding trials, and we were able to achieve cycle times of 155 seconds. So currently, the Ford team is educating the supply base, right? They're creating a supply base. They're using the water assist unit and this particular production intent tool to educate the supply base, educate suppliers, and they're issuing quote packages for a variety of parts, both interior and exterior, for consideration for their water assist injection molding process in future programs. So with that, I say thank you, and I'll take your questions.
Thanks, Dave. We got a number of questions here, and hopefully we can knock them out in the next 3 minutes. I'll start with how accurate can you control the thickness with the water assist?
The thickness was pretty accurate. Once you were at cycle and established a good equilibrium with your temperatures, your tool temperature, your melt temperature, your part thickness was very consistent. There were measurements that I can provide results, after the presentation, but it was very consistent.
Okay, good. And then the next question was, which Ford program vehicle implemented this technology on its crosscar beam? I don't think it was ever implemented. They're looking to implement it. Is that correct?
They're looking to implement, yeah. So it was a production intent tool to be used as a demonstrator of the technology. And again, the technology is currently being used, both the water assist unit and the tool, to educate the supply base so that they can realistically quote use of this technology in the future.
Great. And then the last question, what is the water temperature at injection, and does that change depending on the polymer you're utilizing?
Yeah, so that's a very good question. I don't remember. It's not cold. It's not boiling, but it is heated by the injection unit. But it might come in at like 90 to 100 degrees Fahrenheit.
But it is controlled. It is something you design in, the temperature that it's being injected at.
It is controlled.
Yeah. And do you have a feel if it have to change for different polymers? If you use nylon and polypropylene, but if you stepped up to a higher temperature, would you have to change the water temperature as well?
You, I mean, that's one of the things you can adjust, again, to control the thickness of the part of the wall stock. We really didn't, we set it and let it be in this particular case. at whatever temperature that was, again, probably between 90 and 100 degrees Fahrenheit. But essentially, you could adjust the temperature of the water based on the polymer you've injected.
Great. Thank you. Let me go ahead and end us there because we're at the end of the hour. I do want to share my screen one more time to show that our next presentation, our next webinar is Monday, December 15th. Would welcome you all to join in on that. And then I'd say we've locked down our dates for 2026. So feel free to mark your calendars for all those upcoming ones. I would say we've got our presenters for December pretty much locked in. We've got some good ones coming from NAWA as well as from another nanotube producer, a boron nanotube producer. So excited to have everybody on that. And with that, I'm going to close it out and thank everybody for your time. Appreciate it.